Okay, hello and welcome everybody. Good afternoon to the fourth day of our online workshop on next generation quantum clocks. My name is Eckhard Peik. I'm from PTB Time and Frequency Department in Germany, and it's my pleasure to be the moderator for today, for the afternoon. We have two lectures today on exciting new reference systems for optical clocks. And the first lecture given today is by Piet Schmidt, a colleague working here actually next to me in a different building at PTB. He is also associated or director of the QUEST Institute, an associated institute between the Leibniz University of Hanover and PTB. And he and his group are the pioneers of using quantum logic spectroscopy methods for novel clock systems, for highly charged ions, for example, a very exciting application. And so I'm looking forward to his lecture today, which is entitled Quantum Logic Clock. Piet, please, the floor is yours.
Yeah, thank you very much for the kind introduction, Eckhard, and for the organizers to invite me here. I'm actually not going to stay with the singular. I'm going to tell you about more than just one type of quantum logic clock. I will start with a brief motivation. Now, what is our wish list for optical clocks? What do we want to have? Now, we all know, also from the previous tutorials, that there's essentially two notions that we have to fulfill for an optical clock atom. The first one is we want to have high stability, which means a low statistical uncertainty. And you've probably seen this formula already. The quantum projection noise limit of any clock is roughly given by this expression. So we want an optical transition frequency, we want many atoms, and we want a narrow transition that we can probe for as long as possible to make this number here very small. Now, the other notion is accuracy, the systematic uncertainty. And for this, we require our favorite atom to have a very low sensitivity to shifts or to effects that may shift the line resonance. And there are, for example, collisional shifts that are more of a problem maybe in neutral atom lattice clocks. Then there's Doppler shifts that we need to take into account. We need to be able to cool the system near the ground state of motion. And we require the systems to have a very low sensitivity to external field perturbations arising, for example, through electric and magnetic fields. Now, there's a fairly sizable number of species that have been investigated as candidates for neutral atom clocks, mostly these days neutral atom lattice clocks, as well as ion optical clocks. Now, besides these two criteria, there's actually maybe a third secondary criteria, which is a potential sensitivity to new physics effects that you would like to investigate with these types of optical clocks. That's one of the application areas that has been a driver in the past and will continue to be so in the future, to look, for example, for dark matter or other effects. Now, the question is, in particular, in view of this secondary criteria, sensitivity to new physics, are these species here all that we can investigate? And this is just a subset of the periodic table, the species that have been investigated, neutral or singly charged, or as we continue to increase the charge state along this third direction here, you can see that there's many more systems that we could potentially investigate. So if we start increasing, or if we take the charge state as a variable, then all of a sudden the periodic table becomes three-dimensional, and there's a plethora of systems with potentially very interesting properties that we can investigate. And of course, we don't need to stay fixed with the periodic table. We can also combine elements and, for example, form molecules to start investigating molecules that have their own fascinating properties. To see whether we can actually turn some of these more special systems into optical clocks, we need to have a look at a typical spectroscopy sequence that is typically performed when operating on an optical clock. First of all, we typically start with a laser cooling pulse of maybe a few milliseconds or so to minimize motion and therefore Doppler induced shifts. That's the time dilation shift, for example, or yeah, mostly the time dilation shift. Now, before doing spectroscopy, we also need to perform initial state preparation. Typically, we don't have two-level systems, two-level atoms, but rather multi-level atoms, as is depicted here. And what we usually do is we perform optical pumping, maybe combined with RF dressing to prepare our atom in the target state for spectroscopy. The next step is obvious, it's spectroscopy. So we probe our clock transition for as long as possible. And after that, we're trying to find out whether we've actually made the transition from the ground to the excited state or not. And this is typically done by state-dependent fluorescence, by connecting the lower level here to another excited, a third excited state level with a short lifetime. Now, you may have noticed that for 3 of these steps in the spectroscopy sequence, we actually need a fast laser cooling type transition. For laser cooling, obviously, for optical pumping, and for the state-dependent fluorescence. And now, not all the species that we may be interested in turning into clocks actually have that feature of a laser cooling transition. And this is precisely where the quantum logic spectroscopy technique comes to help. How does it work? Quantum logic spectroscopy has been demonstrated mostly with trapped ions. There's some offspring in the solid state community. But the way we perform quantum logic spectroscopy is that we trap the spectroscopy ion together with the so-called logic ion. And the logic ion, we have full control over. It has, we can control it, we can laser cool it, and we have very efficient state readout of the logic ion. Now, since the 2 ions are together in the same potential well of a linear Paul trap, we can, in principle, achieve a very high accuracy. Since the 2 ions are repelled via the strong Cooler interaction, there's a very strong coupling between them. And if we cool one ion, for example, the logic ion, then the other ion becomes cold as well. This is just like a 2-coupled pendulum, essentially. What we can also do is we can apply a series of laser pulses that maps the internal state after spectroscopy on the spectroscopy ion onto the logic ion, and then detect the spectroscopy result that we've achieved on the spectroscopy ion through the logic ion. So in a way, we can view this 2 ion system as a composite system that combines the advantages of both species. And in fact, we can also control the spectroscopy ion using the logic ion, for example, in state preparation that I'm going to show you later. And this all allows us to investigate previously inaccessible species and systems. Now, just as an example that sympathetic cooling works, this is sort of a more trivial part of quantum logic spectroscopy is shown here, where we have magnesium ions. These are a false color real-time image or movie rather. And you can see voids here in between, and in the voids there's of course also ions that do not fluoresce, and these ions are magnesium hydride plus ions. And the fact that these voids are very well localized tells you that we achieve sympathetic cooling of these molecular ions here. Now, after this brief introduction and motivation for quantum logic spectroscopy, I'm going to show you two examples. I will start off with quantum logic spectroscopy of highly charged ions, and then show you sort of as the crown jewel of quantum logic spectroscopy, the current state of the art in the aluminum quantum logic clocks. Okay, let's start with quantum logic spectroscopy of highly charged ions. Now, when we start removing charges from neutral, from our favorite neutral atoms, then our energy, our feeling for energy scales starts failing us. Yeah? Simply because if we compare hydrogen to hydrogen-like uranium, that is uranium-91 plus, then the binding energy goes from 10 eV to 140 kilo electron volts. The hyperfine splitting used to be micro electron volts in hydrogen, is now electron volts, so it's in the visible spectral regime. QED effects are strongly enhanced also from micro electron volts to 300 electron volts. And at the same time, Stark effects are strongly suppressed simply because the remaining electron orbits in a very close, in a very small orbit around the remaining nucleus because of the strong Coulomb interaction between the highly charged nucleus and the single electron that is left. Now, there's optical transitions in these highly charged ions. Either fine structure transitions can turn into optical transitions, hyperfine structure transitions, for example, here in the hydrogen-like systems are in the optical regime, and then there's also level crossing transitions that add to the richness of optical transitions we can perform spectroscopy on. Now, there's a large number of applications for these highly charged ions. They have been proposed as superior qubits, as optical clocks, and in particular, having in mind the secondary criteria, namely that they're very sensitive, for example, to a change in the fine structure constant. You can also use them to probe for a change in the electron to proton mass ratio. And we plan to perform isotope shift measurements to constrain fifth forces using highly charged ions. Now, to give you one specific example that we're currently working with, that's argon-13+. Argon-13 plus has the electronic structure of neutral boron. So there's a fine structure splitting in the ground state, and then the first excited state in boron is 250 nanometers away. Now in argon-13 plus, we still have the fine structure splitting. This is now in the optical regime. It's at 441 nanometers, and the first dipole allowed transition is now at 19 nanometers. We currently have no lasers to perform laser cooling. Okay, now one question is that you have to ask yourself now, given the list of criteria that I have put forward in one of my first slides, do highly charged ions actually fulfill all these criteria? And of course, we need this low sensitivity to resonance shifts. And actually, there's highly charged ions have actually an advantage here, simply because Stark shifts are strongly suppressed. The second order Zeeman shift is also strongly suppressed, and the electric quadrupole shift, that is one of the shifts in single ion clocks that has to be addressed, is also suppressed in this case. And then we also need to fulfill other criteria. For example, we need narrow transitions, typically, ideally below a hertz, to allow for long probe times. That exists in highly charged ions. We need the clock transition to be in the optical regime. That also exists. And we want, ideally, the atomic properties of our clock ion species to be similar or better than the current best atomic systems for singly charged ions, namely the aluminum and ytterbium ion clocks, and also that can be found in highly charged ions. Also, for practical reasons, we want a sparse or at least simple level structure, and that we can have. We want long-lived isotopes of several years lifetime. That exists, but unfortunately not found in just one single species yet. So you can sort of pick what is sort of your most relevant criteria, and then you can go into the periodic table or into one of these very many publications proposing a myriad of or plethora of highly charged ion candidates for optical clocks with predicted uncertainties of below 10 to the minus 18. But of course, there's not a lot of experimental data available for highly charged ions, and calculations are not in all cases sufficiently accurate to make good predictions for clock ions, and therefore we need more atomic and spectroscopic data. Now, where are we in terms of, or where were we rather, in terms of highly charged ion spectroscopy? Typically, that has been performed in plasmas, so-called electron beam ion traps, where we have an electron beam with a very large energy, and that is focused down onto a gas, and then through electron impact ionization, we generate our highly charged ion species, for example, argon-13+, as it is shown in this case here. So this is fluorescing argon-13+, fluorescing at 441 nanometers. Then this fluorescence is imaged onto a grating spectrometer, and then you get curves like this, where you see a very large splitting because there's a very large magnetic field of typically on the order of a Tesla or so. And then the width of these transitions here is 45 megahertz, because this happens still in the plasma with energies of tens of electron volts, and that's just the wrong unit to describe the kinetic energy in precision spectroscopy, and therefore we have a huge Doppler broadening in these systems and can resolve these lines to within maybe 150 megahertz or so. Now, what is the problem? These electron beam ion traps here, or these compact version that we are using, are not a good environment to perform high precision clock type spectroscopy, and the highly charged ions typically have no cycling transition for laser cooling and state detection. And therefore, ideally, we want them in a Paul trap environment, as is shown here, for example, a linear Paul trap of the Innsbruck style, and we want to employ quantum logic spectroscopy for cooling and detection. So we have set up such a system in a collaboration with Jose Crespo's group at the MPIK in Heidelberg. And we have set up a cryogenic supply line to provide a 4 Kelvin environment for the highly charged ions, simply to reduce to provide a very good vacuum, because any collision with background gas atoms will result in charge exchange and therefore loss of the highly charged ions. We also set up a compact electron beam ion trap using permanent magnets that allows us to go up to highly charged xenon, for example. We then breed the highly charged ions, extract them. They're bent around the corner here. We do a time of flight selection of argon-13+. We then have a first deceleration stage here, and then the ions enter into the Paul trap that we have here. It's a cryogenic Paul trap at roughly 4 to 5 Kelvin environmental temperature, where we have prepared a cloud of laser-cooled beryllium ions, and then we inject the highly charged ion, argon-13+ in this case, that appears as a very large void inside this ion crystal of beryllium ions. And then what we do in the next step is get rid of all the extra beryllium ions that we just needed to for efficient energy removal of the highly charged ion, until we arrive at a 2-ion crystal composed of argon-13+ and a single beryllium ion. And the total preparation time is a few minutes of this situation, and the lifetime is on the order of 3/4 of an hour or so. Okay, and then we can start our quantum logic sequence. And the original idea to do quantum logic with trapped ions goes all the way back to this seminal paper by Ignacio Cirac and Peter Zoller, where they proposed to do quantum computations with trapped ions using the collective motional mode as a quantum mechanical degree of freedom to entangle the ions. And Guido Wilpers has shown you yesterday in his tutorial how that is performed. Now, it was Dave Wineland who had the idea to not only use this for quantum computations and quantum logic, but to also use this for spectroscopy. And this is what I'm going to show you. Now, how can we view this system? And this is a repeat of what Guido has shown you already. We have our favorite two-level atom that can be a clock transition or a logic transition in our logic ion that we can couple using laser radiation. The coupling strength is designated by the Rabi frequency, omega, capital omega, and the excited state lifetime here, or the line width of this transition, is much smaller than the trapping, the secular motional frequency of the ion in the trap. That's depicted here as a harmonic trapping potential, where we have the quantized motion of the ion in the trap. Now, this combined system of motion and electronic degree of freedom can be fanned out, and then we can drive transitions between these different levels. And specifically, if we're close to the motional ground state, we can distinguish between so-called carrier transitions that only change the motional state and do not affect, only change the electronic state and do not affect the motional state. This is what we do for clock interrogation, for example. We can drive so-called blue sideband transitions that change the electronic state from spin down to spin up and put in a quantum of motion. And we can drive a so-called red sideband transition to remove a quantum of motion while going from the ground to the excited electronic state. And all this, we can, which type of transition we drive, we can choose via the laser detuning here, because we're in the result sideband regime, which is exactly this criteria here. Okay, now in our argon 13 plus beryllium plus 2 ion crystal, we can perform exactly these operations on the beryllium ion very easily. We can, for example, drive red sidebands or blue sidebands here. And if you have 2 ions in the trap, then you get 2 different types of motion along the axial direction. One is, we call the in-phase motion, and one the out-of-phase motion, for obvious reasons here. These are the red sidebands of those 2 modes, and these are the blue sidebands of those 2 modes. And now, by knowing the motional frequency of a single beryllium ion, we can calculate by very simple algebra what the frequencies of the combined ion crystal would be, for example, for the in-phase mode. And we can see here that we can clearly distinguish argon 13 plus from the 2 neighboring charge states here, simply by looking at the motional excitation spectrum. So we can also perform ground state cooling of the 2 axial modes by performing this only on the beryllium. And we do that by driving red sideband transitions here and reinitializing to the electronic ground state. And then once you're here, there's no level you can couple to here, and therefore this is a dark state with respect to red sidebands, and therefore you prepare the system near the ground state. And this corresponds to roughly 3 microkelvins or so, and that's probably the coldest highly charged ion in the universe. Now, as the next step now, since we are now in the ground state, we can now perform spectroscopy in principle. And we have prepared the 2 ions in the spin in the electronic and motional ground state, and then we apply the spectroscopy pulse on the argon-13 plus. That's our regular clock probe pulse that in general generates a superposition between the two electronic states. And in any regular clock, you would now simply detect whether you've actually made the transition or not, which we cannot do for argon because there's no cycling transition. Instead, we apply what we call this red sideband pulse that I have introduced to you on the previous slide, that changes the electronic superposition into a motional superposition of the ion crystal being in the motional ground state and the first excited motional state. And since this is a normal mode that is shared between the two ions, also the beryllium is now in this motionally excited state, and we can apply the same type of pulse on the beryllium ion at a totally different laser wavelength, of course, and map this motional superposition back into an electronic superposition, this time on the beryllium, where we can detect it with very high efficiency by doing state-dependent fluorescence detection. Now, we have done that in argon-13 plus, so this is the detuning of our spectroscopy laser. This is the excitation probability, and here you can see the typical sinc function from square pulse excitation. We have a Fourier limited line width of 65 Hertz. We've also put ourselves onto the resonance here and changed the probe time, and then we observe Rabi flopping with a Rabi frequency, and the decay that you see here is strictly dictated by the excited state lifetime of about 10 milliseconds. We've also performed a dedicated lifetime measurement that confirms an earlier measurement with an even higher resolution made in an electron beam ion trap. Now, I should say that all these measurements were only possible because we could lock our spectroscopy laser onto the silicon cavity stabilized laser that is operated by Uwe Ster and Eric Benkler in a third building here at PTB. Now, I was not entirely honest with you. Of course, it's not a two-level system that we're dealing with, but rather we have 6 levels here. We have Zeeman substructure, and to do spectroscopy on all these different transitions, we need to do initial state preparation. And typically, we would do optical pumping, for example, just shining in the green light here. But since the excited state lifetime is 10 milliseconds, that would take a very long time to actually get the system into the target state. And so what you can do instead is quantum logic assisted state preparation, where we apply only coherent manipulation on the highly charged ion, and the dissipation that you necessarily need for optical pumping is performed via the beryllium, or is provided by the beryllium ion. How does it work? We drive a coherent pi pulse from the excited state up here, that's a red sideband pulse, onto resonant to the ground state, but at the same time we excite a motional quantum here that we can take out with the beryllium ion. And since now we're back into the motional ground state, if we apply the same pulse again, it does not change the electronic ground state or the electronic state here, because there's no level that the red sideband pulse can couple to. Therefore, the dissipation via ground state cooling on the beryllium makes this step irreversible. And we can play the same game on all the other transitions. So we can shelve all the excited state population down here, followed by ground state cooling. We can then shelve it up here, again, cool to the ground state, prepare it down here, again, ground state cooling. And then as a last step, we shelve the transition from the outermost Zeeman state onto here. And we can repeat the sequence a couple of times, and then we have a near 100% population of the ions in our target state. And using that state preparation, we can perform spectroscopy on all these transitions as shown here. This is a zoomed out version of the spectroscopy, where we have also plotted the different theoretical predictions. The dashed lines here are just the semi-classical Landé G factors. A full or relativistic Dirac equation is now the violet dashed lines. If we include electron interactions, we see the green lines here, and only if we perform the full QED relativistic calculations, we find agreement between the theoretically calculated G factors with our experimental data. And using these type of spectroscopy, we can now measure ground and excited state G factors with a resolution below 10 parts per million. Okay, we've also operated the argon-13 plus as an optical clock by locking our laser frequency to these 4 components here, probing left and right of the excitation profile to determine the center frequencies here. And you can see the 4 servos in different colors running here over maybe 16,000 seconds or so. If we plot the Allen deviation of this, we can see that there's drifts, for example, the step in the magnetic field that occurred at about 8,000 seconds. That leads to the drifting off here. But if we take the average frequency of all the Zeeman components, then we're free of this magnetic field shift and have a very nice, we continue to average down here very nicely. Okay. Now, where does that put us on highly charged ion spectroscopy? Here's the historic values for argon-13 plus measurements over the years. You can see that the best values were on the order of 10 to the few parts and 10 to the minus 7 or so. Then there was a more recent measurement in Sven Sturm's group at the NPRK in Heidelberg in a panning trap. And then our measurement is down here. We're currently at roughly 0.3 Hertz resolution or so. And we're aiming to extend that into the future here. We're currently working on evaluating all the systematic shifts of the argon-13 plus clock, so to speak. And we then want to perform isotope shift spectroscopy of argon isotopes, perform absolute frequency measurements, and then do calcium isotope shift measurements. Before we will address the first real clock candidate, which, for example, could be nickel 12 plus, which has a very long-lived clock transition that is optically addressable and has very nice atomic features for a clock. Okay, now where does it put our argon-13 plus clock in the context of other atomic clocks? In this plot, you see the evolution of the cesium clocks in blue and the evolution of optical clocks here on a much steeper slope. And our argon-13 plus clock, if you so wish, is located here. But be aware, this is not yet accuracy. This is just resolution at this point, because we have not evaluated all systematic errors yet. But obviously, there's still a large gap here to the currently best optical clocks, which is this data point here, which is the aluminum optical clock that I am going to talk about next. So the idea of using aluminum as an optical clock candidate dates back to Hans Demelt, actually, who proposed aluminum in 1992 because it has a number of very interesting features that suggest it as an optical clock candidate. First of all, it has a fairly narrow optical clock transition of 8 millihertz, roughly 20-second lifetime of the excited state at 267 nanometers. The reason why Demelt in particular proposed aluminum was because it's a 0-to-0 transition, so there's no first order electric quadrupole shift in this transition. And that Demelt did not know that, but as it turns out, aluminum has one of the smallest blackbody radiation shift coefficients, so the polarizability is very small in aluminum. That's another very good atomic property for a clock, of course. However, there's no cooling transition. very similar to the highly charged ion case. The cooling transition is in the deep UV, where we currently do not have lasers for cooling and detection. Now, how the sequence looks exactly the same compared to the highly charged ion case. To do the state transfer, the entire sequence starts with laser cooling of maybe 15 milliseconds all the way to the ground state. Then there's internal state preparation, and then the clock transition is probed between 100 and 300 milliseconds. And after that, the state detection is performed using a scheme similar to the one that I have shown you for the argon-13+ case. Now, together with optical pumping and interleaved measurements, the duty cycle is on the order of 50% in this latest incarnation of the aluminum clock. Now, state preparation is in this case performed via the triplet P1 transition that has a lifetime of 300 microseconds, so it's moderately short-lived, and you can actually do optical pumping in along the lines that I have shown you earlier, where you just rely on spontaneous emission and then pump it between the two stretched MF states here in the electronic ground state. You then perform spectroscopy on the two outmost components, for example, and then the average frequency is free of the first order Zeeman shift, whereas the difference frequency is proportional to the magnetic field that you need for evaluating second order Zeeman shifts. Now, this generation of aluminum clocks at NIST is operated with magnesium as the logic ion species. And on the next slide, I want to show you another feature of quantum logic spectroscopy, which is a very efficient state detection scheme. Now, after probing the clock transition, the motional mapping that I've shown you on the argon-13+ we've also implemented on the clock transition, is done in the aluminum case on the triplet P1 transition with a much higher Rabi frequency, so it's much faster. And what you learn from that by mapping it over from the aluminum to the magnesium ion, where you can detect it, is whether there's still ground state population or whether there's no ground state population any longer, by simply applying, for example, a blue sideband pulse here that puts in a quantum of motion only if the aluminum is still in the ground state. Now, the beauty of using quantum logic spectroscopy here is that you can actually repeat this measurement process. Yeah? You can then do a state-dependent fluorescence on the magnesium, but you can do that several times, this mapping pulse. And during the mapping pulse, you're not going to change essentially the ground state population here, so you can repeat it, and you can use a special technique that's called Bayesian inference of the detected photons on the magnesium ion that I don't have time to go into detail. And if you do that, then the error probability of detecting the ground or the excited state here is dramatically decreased here down to a level of a few parts in 10 to the -3, actually. So that's a threshold likelihood ratio. That's sort of a parameter that tells you when to stop the repetition here, because you have enough information about the internal state. So that's a sort of when to break the loop here of repeated measurements. And as you can see here, that agrees very nicely with the error probability here. And on average, with 6.5 repetitions of the sequence, you can get 99.94% error probability, such that your signal to noise is no longer limited by the detection. And using this technique, the NIST group has performed spectroscopy on this latest incarnation of the aluminum clock. And they have evaluated all systematic shifts down to a level now of 9.4 times 10 to the -19, which makes it the most accurate clock that currently exists. Now let's have a brief look at the error budget here, what are the dominant contributions. There's still excess micromotion as a significant contribution here, so nulling of electric fields is a problem. Then black body radiation is a problem. This is strictly dominated by the polarizability, the known polarizability or differential polarizability of the two clock states here. Then there's a quadratic Zeeman effect, which is also limited by the knowledge of the involved G factors. Then there's secular motion and background gas collisions. Now there's another very interesting shift contribution, which is the first order Doppler shift here, that you would argue should be absent in any system that is operated deep in the Lambdicke regime, where you have recoil-free absorption, so you do spectroscopy and essentially the motional state is not changed. But what this group did is probe from two different directions with counterpropagating clock laser beams, and then they observed a shift or a difference in the center frequency here of almost 5 times 10 to the minus 17. That is very large, but if you average both directions, you should then come to 0, and the residual uncertainty of this cancellation is given in this number. Okay, now they've also performed a frequency comparison with the terbium optical lattice clock that is operated at NIST, and the result is shown here, where you can see that for long averaging times, the statistical uncertainty goes down as 1.2 times 10 to the minus 15 divided by the square root of the averaging time. Now, the red line here is the fundamental aluminum plus clock limit when you probe it with the excited state lifetime. And the natural question to ask is, so what keeps us from achieving this limit? And the reason is that we need longer probe times to achieve this. We need to actually probe at 20 seconds. For this, we need the best lasers that we can get, and even better, to maintain laser coherence during these long probe times. But another issue that we will very likely start having is motional heating of the system during these extremely long probe times. And let me just very briefly go into details why that is a problem, in particular in quantum logic clocks, and why we can also solve this using quantum logic very efficiently. Now you've seen this illustration here already, that we have two axial modes, in phase and out of phase modes for two ions, and then obviously in the radial directions we also have 2 times 2 modes. So overall we have 6 motional modes that need to be cooled to reduce the second order Doppler shift. Now if we now look into this plot, this is a bit busy, but I'll walk you through this. What you see on this axis here is always the mass ratio between the logic ion and the spectroscopy ion. So yeah, and the epsilon here is the ratio between radial and axial trap frequencies. And so if you go towards smaller epsilons, then the crystal becomes unstable and starts tilting from an axial configuration into a radial configuration, the lower you go in this epsilon squared here. Now, what you see in this upper plot that I want to focus on is the mode parameter B1. And that tells you how large the amplitude of one of the two ions is with regard to the other ion. So the B1 squared plus B2 squared, these are the two mode amplitudes of the two ions, is always 1. That means if you're operating in this regime here, then one ion has a very large amplitude, for example, the spectroscopy ion, and then the other axial mode, the logic ion has a very large motional mode amplitude. And you see here in the axial direction, it's a very smooth function, and there's across the mass ratio, there's always enough amplitude to actually perform very efficient cooling, because obviously the mode where the cooling ion has a very small amplitude, this, for example, that is cooled very poorly only, yeah, a very small cooling rate. In the radial direction, however, the situation is very different. Here, the transition is very steep, and you need to operate very close to a matched mass ion crystal to obtain efficient radial cooling. Now, in principle, this is all not a problem if it not were for additional heating rates that you have in your ion crystal. And in the presence of those heating rates, of course, you get different steady state temperatures. If you apply Doppler cooling at the same time. That's the situation that I'm showing here. So here's the second order Doppler shift, for example, for the aluminum ion clock here, using different logic ion species for cooling. And then what's plotted on this axis here is the heating rate that you have, sort of the anomalous heating rate that you have in your ion trap. That is increasing in this direction. You can very clearly see that terbium, which is very heavy, is a very poor choice as a logic ion species, whereas the lighter you get, the better it becomes. And what's also interesting is that the beryllium case here, where we have a 9 to 27 or almost a 1 to 3 mass ratio, is still very efficient for reasons that I can tell you if you're interested in, or you can read it up in the paper here. So what we learn is you want a light, so you want either a logic ion with almost equal mass as your aluminum ion, or lower. You want a small heating rate in your trap, and you probably want simultaneous cooling during the long probe times of maybe 20 seconds that you can actually achieve using the quantum logic spectroscopy scheme, because cooling on the same ion would of course destroy the coherence of your clock interrogation, but you can cool on the spectroscopy, on the logic ion here simultaneously, or simultaneous to the clock probe time here. And therefore you can reduce systematic Doppler shifts significantly. Now, I don't want to go into details. We've developed a so-called double bright EIT cooling scheme that is very fast. You can see it here compared to sideband cooling techniques. And this is the radial mode that we can cool very efficiently, and the axial modes we can cool very efficiently. And we can cool those modes simultaneously with just one pulse. And as it turns out, in an aluminum calcium ion crystal, and we're using calcium as a logic ion species in our system, all modes bunch up such that we can cool all 6 motional modes simultaneously using this double EIT cooling technique. Now, let me finish by telling you the status of our own PTB quantum logic clock with aluminum. We have a sapphire titanium trap, so the blade material is titanium, and we have sapphire discs to mount them. We've performed together in this Ampere collaboration with the CMI in Prague a temperature evaluation, such that just from the uncertainty of the temperature, the black body radiation shift is extremely tiny. We've also implemented this double EIT cooling scheme to reduce the second order Doppler shifts, and we started evaluating the entire system based on measurements using calcium with very low uncertainties. And just recently we've improved the excess micromotion compensation and measurement, such that we're now very well into the 10 to the minus 19 regime in the shifts that we've looked at currently. We've also run, we've also scanned the clock transition. We've observed line widths below 15 Hertz for width half maximum here. And the only thing that's keeping us from operating it as a clock is the limited lifetime of the ions in the trap. And so we have a vacuum upgrade in progress to prolong the lifetime. And this is a picture from last night where the system was last open. We have now a reflector for phase stabilization of the clock light. We have ablation targets here, and we've replaced all leaky windows that we have to improve the pumping rate of the system, such that we hope to get longer lifetimes than the 20 minutes on average that we've observed in the past. Now let me wrap up here. I hope I could convince you that quantum logic spectroscopy is a very powerful and versatile technique that not only allows you to investigate previously inaccessible systems, but also adds feature to your clock, such as internal state preparation and sympathetic cooling and monitoring of systematic effects while operating the clock. I've also shown you that we now have an aluminum clock with very small systematic uncertainties, and then other systems are under investigation, for example, highly charged ions, but also molecular ions that I had no chance to talk about. We started, and others have followed up, started investigating and performed rough quantum logic type spectroscopy on. So all in all, I hope I could convince you that quantum logic spectroscopy has a very bright future, and that there's a lot of room at the bottom to be explored. And with that, I would like to thank my fantastic group and you for your attention.
Thank you very much, Piet, for the interesting lecture. So the lecture is open for questions. If you would like to ask a question, please raise your hand, and I hope I can see it and open the microphone for you. Maybe as long as you are collecting ideas, maybe I start with a question. Piet, you mentioned the wide choice or the broad range of applications of proposals for highly charged ion clocks, and you mentioned also that there was maybe not all the candidates for fulfilling all the wishes on the list, but you mentioned that you like nickel 12 plus. Can you say a little bit about it? What type of transition this is, and what makes it interesting?
So it's also a fine structured transition in this case in the optical regime. It's a transition between triplet P0 and triplet P2. Therefore, the triplet P2 will have an electric quadrupole moment, but it is expected to be rather small. Of course, black body radiation shifts are strongly reduced, and we're operating at 4 Kelvin anyway, so that black body radiation is not an issue. The other interesting feature for nickel is that, in contrast to the argon 13 plus that we've investigated so far, the excited state lifetime is on the order of 20 seconds or so. Which allows us much longer probe times and therefore a much lower statistical uncertainty, and may enable us to actually reach comparisons at the 10 to the minus 18 level within a reasonable amount of time, which means days, instead of years.
Mm-hmm. What's the clock wavelengths?
Okay, now you caught me off guard. I think it's
it
around 400 nanometers or so.
400 nanometers, okay. Okay. Please raise your hands, or I'm looking if I see any open questions.
So either it was very clear or incomprehensible. I hope the first.
I'm sure it was. I'm looking through the list. There is one. There's one connection in the chat. Okay, no, it seems like we have no questions here. So yeah, I think please feel free to contact Piet Schmidt by email if you would like to learn something more from him. So thank you very much, Piet, for the lecture. And
thanks for having me.
with this, I like to close the seminar and invite you all to reconvene for the second lecture this afternoon on the thorium nuclear clock by Thorsten Schumm. So see you soon there.
Thank you very much. I'm going to end the meeting and I will see you in the next seminar. Bye.